In this video, we'll discuss how we determine where a function is increasing and decreasing. Recall that we've already defined what it means precisely for a function to increase and to decrease using calculus, that is, using the notion of derivatives. We saw this from geometry. And given any function, it could go up and down over its entire domain in different intervals. And so recall that in fact, we saw that if the derivative of a function is positive, that means the function f of x is increasing. I'll use an up arrow to indicate increasing on whatever interval, for every point in that interval where the derivative is positive. Okay? And similarly, we saw from geometry that if we take the derivative and it's negative, then the function f of x is decreasing or going down for every point in some interval where the derivative is negative. Okay? So whenever the derivative is positive, the function is increasing, and wherever the derivative is negative, the function is decreasing. Again, a given function may go up and down throughout its domain, and so we'd like to come up with a very precise way of determining exactly where a function is going up and where it's going down without having to check an infinite number of points. Okay? And it turns out there's one very nice way to do this. In fact, we're using the power of calculus to determine the behavior of the function over its entire domain. So now I've drawn a picture of a function, f, in red. And let's use geometry to come up with a very systematic way to determine exactly where this function's increasing and decreasing. Okay, we already know the precise definition of what it means for a function to increase on an interval and decrease on an interval. Let's use the power of calculus to come up with this systematic way of determining where a function is going up and where it's going down automatically. Okay? Now, this function is drawn very nicely. We already have the picture. So we all would agree on where this function is going up and where it's going down. That's easy. But it turns out that once we develop the geometry here, and using calculus, of course, we'll be able to extend this to any function, even if I don't have the picture. Also, notice that this function has a very small domain. I've drawn this function to only exist between points a and d, right? Between x values a and d. But of course, the function could extend even further. And in that case, we would be at this forever, looking for where the function goes up and goes down. Again, let's use geometry and the power of calculus to come up with a systematic way of determining where this function is going up and going down for any point in its domain. Okay? So let's just think about this for a minute. Think about slopes of tangent lines. That's the key. Well, look what happens. At point B, if I draw the tangent line here, notice the tangent line has a flat slope, right? That's something very special. Same thing with C, right? C has a flat slope there as well if I draw the tangent line on the curve at that point. Now, notice also that the function clearly is increasing between A and B, right? We can see that. That as we plug in points, x values from A to B, the corresponding y values are going up. So we've already seen, by our precise definition, the function's increasing here from A to B. So over this interval, the function is going up. And I'll write f of x is going up. Similarly, we can clearly see the function is going down between B and C. Again, using our precise definition, we would know that's true, right? For every x value that we're increasing, the corresponding y values are going down, decreasing. But even if we just look at it, it's pretty clear, right? So I'll draw that. So f of x is decreasing here. And we see that the opposite happens between C and D. The function's again going up, right? Using our precise definition, and of course just our I. We know that f of x is going up here. Okay, so this function is going up, down, and up again. But notice that in fact, at these sort of places where it's transitioning, okay, I've drawn a tangent line and it's flat. Okay, that's a very, very special point. It's a transition point. The function is transitioning from going up to going down, or from going down to going back up. Okay? And those particular places, well, the geometry of the tangent line is very important at those places. And this is always going to happen. Well, for most cases anyway. That is, you see, if we have flat tangent lines at those transition points, what does that mean for calculus? Well, we already know, if you recall, the derivative of a function tells you the slope of the tangent line of the function at that point, right? So look, these two lines that I've drawn have a slope of 0, right? There's no slope. They're flat. 0 slope. Let me write that down. 0 slope. Okay, that line and clearly that line. Okay? That means the derivative is 0 there. Isn't this great? Okay, this is using calculus. So that means if the slope is 0, that means that at this point the derivative of f is 0, and at this point the derivative of f is also 0. Well, we can be a bit more precise here. What I mean by that is that the derivative of f at b is 0, and the derivative of f at c is 0. Okay, I'll write that down here. F's derivative at the point b is 0, and f's derivative at the point c is 0. Okay, slightly abusing notation, but the point is that the slope of the tangent line is 0. So these places, these transition points where the slope changes from going up to going down or down to up, are places where the derivative has a 0 value. Okay, these are very special places. And in fact, we can say the function is doing something critical at these particular x values. Let's look at another example. Here again, I've drawn the picture of a function in red, but the function looks a little different, right? This time, the function has sort of these cusps, right? These sharp edges at the point b and c. Again, I can just analyze the function by looking at it for a minute, knowing in the back of my head our precise definition of an increasing and decreasing function. And clearly we can see the function is definitely increasing. I'll say f of x is increasing from a to b, right? As we move along in positive x, the corresponding y values are going up. Similarly, between b and c, the function is decreasing, right? It's clearly going down. And also between c and d, the function again is increasing. Okay? This is a function that is definitely continuous, right? But the thing about it is, recall from our definition of derivative that a function is not differentiable at edges, right? And we saw why that's true. In particular, we can see that even though this function is increasing and decreasing over different parts of its domain, it's defined everywhere, it's continuous, it still is not differentiable everywhere, right? So it turns out that a function can transition from going up to going down even at places where the derivative doesn't exist as well. Okay? These are also important points in the life of a function. Okay? In particular, these will also help us determine the intervals of where the function is going up and going down. Okay? So in other words, we say the function is also doing something critical at these places as well. Notice here I can't really draw a tangent line because the derivative doesn't really exist here and here, right? We can't differentiate the function. So we'd say that clearly f of the derivative of f, I should say, does not exist. Okay, I'm shorthand as dne. The derivative does not exist here and here, okay, at these two places, because it's a cusp, right? It's a sharp corner, and we know that from before. So that means that, more precisely, I can say the derivative of f of x does not exist, I'll say, does not exist, at the x values, x is b, and the x value, x is c. Okay? These are two other kinds of critical values, critical points in the domain of a function. They're transition points, ultimately. Okay? And they give us another possibility for when the function might transition from going up to going down. So it turns out that we have to look for places where the derivative is 0 and where the derivative might not exist.